implementation of binary trees. So can I implement a binary tree with the help of an array? For example, suppose I have uh, a binary tree, something like this. So I have A, B, C, then let's say D, then E, then I have F, G, or maybe then from this E, I have a G, and then let's say H, and from this G, I, J, something like this. Right? I want to implement this binary tree, but can I do it using an array? So array is what? Array will be the continuous memory locations, right? Uh, how many nodes do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 nodes I have, right? But if you see that there are few places where there are supposed to be few nodes, but they are missing out, right? So these are the nodes that are missing out. Here is another one that's missed out. Is another two nodes. They are missed out. Missed out in the sense, missed out from being a complete binary tree. Okay. So if this is the situation, then we will be considering those empty spaces as well. Those are missed out nodes that I'll also consider, but and I'll also consider them in an array, but uh, I'll make it an empty location there. Right? For example, so I'll be doing this, I'll put 0. This is 1, 2, 3, 4, 5, 6, and then 7 and 8 are the empty. Then 8 will come at the ninth location, and then 10, and then 11, 12. This will be 13, this will be 14. So I'll be having locations like this. I'll have A here, then B, C, then D, E, F, G, right? But H I'll have in the ninth location. H I'll have in the ninth location, and then I and J I'll have the 13th and 14th location respectively. Right? Now, what is the purpose of doing this? Uh, implementing a binary tree means that if I have to access everything in this tree, right? If and when required, I have to access every node of this tree. Right? I will be calling this tree by this root. So if someone gives me the root of this tree, then from this tree I can directly go to any of the nodes in this tree. How am I going to go there? Mm, any idea? So if I am suppose I'm at this node, how can I go to the left child of the C? So suppose I am at this in the array, I am at this location I, right? And I want to go to the left child of this. What would be the location? Yes, I'm arranging them level wise, but also I'm skipping few of the locations as well, where there's supposed to be a node in a complete binary tree, but in this particular binary tree, there is no node. Those spaces I'm leaving out. Right? Now, suppose if I'm at this location, I'm at this node C. C is in this one, right? Can you tell me what is the left child of this? Left child is F, right? How can I go from this location 2 to this location 5? What operation I have to do? That question I'm asking in general. So suppose if I'm at the location I, this I means this is a location of the array, right? What would be the location of the left child of I? So for 0, left child is 1. For 2, the left child is 5. For 6, the left child is 13. Can you see any pattern over here? Okay. So the left child will be twice the location of I plus a 1. Yeah, so like to n not n. N generally we take when I have n would denote the number of nodes that I have in the tree. Right? Similarly, if I have a right child, then what would be the location of the right child? It's like just next to the left child, right? So it will be 2i plus 1. Hmm. Now the interesting. So if I have uh, if we are at this node I, then what would be the parent of this? So parent of let's say 6 is 2, right? Parent of 5 is also 2, right? It will be, you can get it from this formula, I minus 1 by 2. Right? And take the floor of that. In this way, I can, yes, I can go to, from starting from the root, I can go anywhere in the tree. Okay. Oh, right. This is the array implementation. This is the array implementation, but we in general what we do, we represent this by a linked list. So every node of the linked list has to have is of this form. What is the form? So what are the things that I need to know? Yeah, actually, so like I took the, it's not 6 minus 1 by 2, it's 5 by 2, it's 2 point something. And then I'm taking the floor function, right? Uh, just recall what this floor function is. Floor function is the integer just less than that number. 5 by 2 is 2.5. What is the integer just less than 2.5? It's 2. Right? That's why so that's the floor function. And the ceiling function is just the next integer. like this. Okay? That's why we have put this. Okay. So in a linked list, what are the things that you need to know? I need to know what is the if I'm at some node, I need to know what these three things basically I need to know. What is the left child, what's the right child, what is the parent of it. Right. Now for each of this, I'll be storing some pointers for it. Right. This will be having parent pointer, right? This will be having left child, pointer to the left child, pointer to the right child, right? And in this part, we'll be storing the actual data or key values that we need. Okay. So if I have so for the root, what would be the parent pointer? Parent of the root. What is that? It will be null. There is nothing. Root is the node from which everything is starting, right? So this root does not have any parent, right? That's why you are setting this parent pointer to be null, right? For if this is the root, if this one is the root, then this will be null, right? And then we'll have a pointer to the left child of this. And again, this will have three pointers to it. I can have a pointer to the right child also, right? Let, uh, this is how these every node will be stored using a linked list. Okay. So parent pointer. So this is again right child is this way, right child is this way. What is the parent of this node? Parent of this node is this one, right? So I'll be having a parent pointer directly going here. Same for this one. Parent of this is this one. Okay. So I'll be having those overlapping connections for every, not for every pair, but in this tree, I'll be having those type of pointers. So that allows me to go from any node, I can go to its parent, I can go to its left child, or I can go to its right child. Right? In that way, I can access every node of this tree. Okay. Any questions? E- Yes. Can you repeat what you just said? This parent pointer is the greatest greatest integer function. Is this clear? Okay. Any question? Uh, oh, these type prove this node structure. So, what are the things that we need to do when we are traversing through a tree, right? So, if I am at some node, I have to go to three locations that are just next to it. One is its parent, another one is left child, another one is right child, right? So that's why we must be having 3 pointers for every node. Right. So if I have some tree, something like this, let me take a small tree, something like this, B and then C. And this one, let's say, has another right child T. Okay. So where should this A come? A will be, so A is the content, right? So A is the data that we have here. B will be coming here. Then C will be coming here, right? And what would be the left child of B? So this is the location where I should be having, this is the pointer to the left child of this particular node. In this tree, if you see, there's no left child, no right child. So what should I put here? The pointer, this pointer should be again null. This one should also be null, right? And the parent pointer should locate, should point to the above, right? So yes, empty, but we don't call it empty. We just didn't point it to null pointer. We say it's a null point, right? So left child of C is also null, but right, there is something in the right child of this, right? Again, there will be a node which will have these 4 components. Parent of this one will be, parent of this one will be going here, right? The right child of C will be this one. And again, the left child of the, what is the entry here? D. And both the left child and the right child will be null for this one. Okay. This is the representation of this particular binary tree using a linked list. Oh, so A should come here. Is this clear now? Okay. Fine. So now we'll talk about this binary search tree. What is this binary search tree? This is a binary tree, as the name suggests, this is a binary tree, but that has another property to it. We call it, it's a binary tree plus a property that we call search property. Right? Okay. Let me tell you what this search property is. Binary tree we know, but now let me clarify what is this search property. This says something like this. For a node X, all nodes in the left subtree, so X is any node, right? So then I look into the left subtree of X, left subtree of X are all the nodes that are in the left subtree of X, all of them should be less than uh, X, right? Um, so no, it doesn't have 2 pointers. This is having every node in this linked list is having 3 pointers. You can define any complicated structures using linked list, right? So the simplest is the linked list that we always talk about, having only 1 pointer. It's the next pointer, right? You can also have doubly linked list, right? I don't know what do you call this type of linked list, but these are in general we call them linked list only. Okay. But note that it's not having two pointers, it is having three pointers. Parent pointer, left child, and right child. Okay. So what is the search property for the node X? All node in the left subtree of X are less than X, and all nodes in the right subtree of X are greater than X, right? Okay, so for example, let's say I have a root somewhere here. So all the, it says everything that I put here that should be less than 10, and everything I put here that should be more than 10, something like this. Let's say I have 4 here, I have 1 here, I have 5 here, and let's say I have 16 here, then so I have 17, another one, I have 21, let's say, something like this. Okay. So this is the right chain. Okay. See, this property is true for every node. Even for this node 16, it does not have any left subtree, but if it, like for this node, that property is automatically true. And everything in the right subtree of the 16, that's more than 16, right? Which is true for everything. So it's a 4. The left subtree is having only one node, it's just one, and the right subtree has having again having one node, it's this. Okay. Fine. Any questions? Yes. So can you tell me how how high this tree can be? Okay. So okay. Suppose this is the case, right? I'll talk about the height of the tree in a moment, but so I'll talk about the height in a moment. But this is an example of a, of a binary search tree, right? Now, I stored these nodes in this way, right? And now, what is the benefit of having this? So, what are the operations? So, in data structure, as I said, the operations that we'll be doing, we'll be discussing those operations, right? So, searching. Let's say I want to search for an element. Right? For example, I want to find whether in this tree I have 17 or not. How do you proceed about searching this? Voice is somewhat disturbing. Um, okay, let me tell you what we should do. So, this tree, how can I not BFS? Okay, so I know what is the root here, right? So first thing, I'll compare the element that I'm looking for with this root. Okay. So if I see this matching, then we're done, the element is present. If that is not there, if x, like this is, suppose I'm looking for, let's say this k is the thing that I'm asking for, right? So if the root is not same as k, then I need to know where should this k be. If this element is at all present there, where should it be? That is the question I have to answer. And the answer is actually in this search property itself. What is the property? Property says that all the elements that are to the right subtree that are greater than the root and the left subtree, everything here is smaller than the root. Right? And now I see this element is actually greater than the root. Now, if that element is at all present there, it must be, because of the search property, it must be coming in the right subtree. Okay. So then what I do from here, I'll go to the right child of this, and now I'll compare this one with this one. Okay. So if they matches, then we are fine. Otherwise, I'll compare them. The element that I'm looking for, it's still more than 16, more than this node. So I'll be moving to the right child again. Right. Now see, I have actually found this element. Okay. Now suppose instead of checking 17, I'm looking for 18. So what should I do? Compare this with 10. 18 is greater, so I'll be going to the right child of this. I have 16, right? I'll be going to the, where should I go? Again, 18 is more, so I'll be going to the right subtree, right child of this. Now I see 17, 18 is more, so I'll again go to the right subtree. Then I have 21. Then I am supposed to go to the left part of it. Left part of it. But here I see, what is this? This is null, right? So because of the search property, if that 18 is at all present there, it is supposed to be in this portion, right? But since we have null here, so I'll say that this is not present. Okay. So again, for example, let's say I want to check for 5, right? So I'll compare 5 with this. 5 is less. I'll move to the left subtree, and then I'll see 4. I'll go to the right subtree. Here I found this element. Okay. Is this process clear? Okay. So how much time does this searching take? So if we have um, if I have a binary search tree, are we going to take O of n time? N is all the nodes, number of nodes that I have. N is basically number of nodes that I have. Are we really checking all the nodes? O of n means we are checking all the nodes, right? But if you think carefully that we are not checking all the nodes. So when I'm looking for 18, I'm moving to this. That means this whole part I can ignore. And on the other hand, like when I'm looking for 5, I'm actually ignoring this whole branch of it, right? So the running time of this one will be not not of O of n, rather I'll say it's something like this. Its running time will be height of the tree. Okay, so it's better to always say yes. So it's better to say that the the running time of searching in a binary search tree is O of h. H is the height. I am I'm about to tell you what is the height of this binary tree, but for this moment, I want you to express everything in terms of height of this tree. Okay, fine. Is this clear? Why it's height is searching takes O of h. Okay. Suppose I'll do another one. I want to find the minimum element of a binary search tree. Where should this minimum element be? It's actually to the extreme left, right? So is it going to be a leaf node? It's true, like it's extreme left. That's correct, but yeah, maybe or may not be. It's may or may not be a leaf, right? Why am I saying so? It's if I just change this one. So what's the minimum? I'll like put one more here. That's a two, right? This two I'm putting it as a right child of one, right? So in this case, see like nowhere I'm violating the search property. Right? But here this one is the minimum, but it doesn't have, it is not a leaf anymore. Okay. Yeah. So how do you find the minimum element? If I give you the tree and ask you find the minimum element, so how do you find the minimum element? You start with the root, go to the left. Again from that, go to the left. Again from that, try to go to the left. Right? How long you should go? Till you hit a null pointer. You keep going to the left till you hit a null pointer. At that point, if you hit a null pointer, then you say that I have actually got the minimum element there. Okay. So again, what's the running time of finding this min? Running time. Again, so I have to go to the left, to the left, to the left. I'll keep going down, right? So I might go actually the height of the tree. Okay. And similarly, like finding max, it's the rightmost node, right? Rightmost node means like from this root, you keep going to the right, to the right, to the right, till you hit a null pointer. That will tell you what the maximum element is. Again, that will also take O of h time. Fine. Now let me come to the interesting part here. Uh, Inserting. So suppose I want to insert a node here. Let me take an example, a larger example. So, maybe something like uh, in this page. Let's say I have 15. Okay. Let's say we have something like this. Now, we talk to the insert operation. Uh, can you tell me, uh, suppose I want to insert, let's say 13, not 13, no, 14, let's say. I want to insert 14. Where should I put this element 14? So I have to be careful about the search property. Right? So search property tells me that, yes, it will come to the right side of it. Search property tells me that this 14 should be in this branch, right? And also comparing the 6 and 14, I can tell it should come in this branch. Again, comparing the 7 and 14, I can tell it should come in this branch. Again, I compare this and I'll tell you like it should be coming somewhere here, right? So again, the process it's somewhat similar, right? I have to compare. So basically I am doing something similar to searching. First, I have to search for this element 14, and searching will take me at the like all the way down till to some null pointer, right, till this point, and there I should be inserting this node. Okay? So I'll keep, again, the process is somewhat similar. I keep on comparing them with the node depending on its value. If the value is more, then I'll be checking with the right child. If the value is less, then I'll be checking it with the left child. Right? Like this, I'll do. And since this process is similar, the running time will also be O of the height. Okay. So now let me ask you this question, that what could be, so if I have, let's say, these elements here, right? What if we insert again for the second time? Yes, it depends on this property, right? Okay. So if you are allowing some nodes to be equal, then you have to adjust here. So here I am saying it's a less than and greater than. Here I have assumed that all the elements are distinct, right? But you can do it in other way also. You can, if you are allowing uh, some elements to be same, so you can change this property something like this. You can say less than or equal to. If the all the nodes that are to the left, then they will come, then they are less than or equal to x. And the other part will be strictly greater. So if you follow that search property, so the moment you come here, you go here, right? And then now, if you want to insert it, it's equal. So again, you will come at this point. Okay. So I should have told you that that's the assumption. Uh, what if I want to insert 8? Okay, let's try do that. Okay, so I compare 8 with this. No, it's smaller. So I compare 8 with this. No, it's greater. I compare 8 with this. So where it's more. So I'll compare 8 with this smaller. I'll go to the left. I'll compare 9 with this, and 8 is smaller. So I'll be having 8 somewhere here. Okay, clear? See, this search property is not violated anywhere. Let's okay. Any other question? Can I insert 14? Can we insert 14 on both sides of 14? Mhm. Okay, so it depends on what you are taking as your search property. See, everything here, this is a special way of storing the data, right? Now, if your data is something that where this repetition is allowed, then you have to set this property accordingly. Okay, so if you I'd say like if you define it something like this, then the equal element will always come to the left. You can define it in the other way. The left part, you can say they are strictly less, or here in the right part, you can say equal elements will come to the right. You have to take either one or this. Okay. So, but you should not be doing the left subtree contains all the elements that are less than or equal to x, and also the right subtree is containing all the elements that are great. Sorry, not sorry. It's I'm saying the something wrong. But you should not be doing something like all nodes in the left subtree are less than or equal to x, and all nodes to the right subtree are greater than or equal to x. You should not put equality in both the sides. You first fix your rule and then accordingly you build. And while fixing, you allow equality either to the left subtree or to the right subtree, not to both. Does this answer your question? Okay. Yes. Okay. So this insertion again takes O of h time. Now let me ask you this. How big the height of this binary search tree be? Suppose I have suppose we have a binary search tree with n nodes there, right? What can you say about the height? So, for example, let's say I'll take a small simple one, right? Uh, so let's say we have these 7 elements there. Okay. What can you say about, so can you think of a binary search tree whose height is small, or how small can it be? Its height is 3. Yes. So in that case, what would be the root? Root I'll take as 4. At the left part, I'll be having 2. What would be the right child of 4? Right child of 4 will be 6. This will be 1. This will be 3. This will be, sorry, not this is not 7. This is 5. This is 7. Right? It is something like this. Oh, by the way, so height of this is 2. Height is not 3. Height is 2. It's a level 0, level 1, level 2. Right? Height is 2. Okay. Uh, so I can have something like this. What type of tree is this? It's a complete binary search tree. Okay, obviously it's a binary search tree. It has this property. This is also a complete binary tree. Right? So complete binary tree, as we have seen before, that the complete binary tree has height. If it is having uh, n nodes, then its height is log n. Right? I'll say it's a O of log n because it's a n minus 1 by 2, something like this. Right? I'll say it's a O of log n. Right? But at the same time, I can have, is it necessarily complete? No, I'm just trying to, it may not be complete actually. But the example that I have taken for this, it's supposed to be complete. Right? Because if you see, in this one, I have taken like 2 to the power 3 minus 1. These many nodes I have taken intentionally. Huh? So that it becomes a complete binary tree. But in general, it's very close to. So if you want to minimize the height of a binary search tree, you should try for a tree which is close to complete binary tree. Okay. And if you do it for sufficiently many nodes, then this height will be O of log n. But the point I want to make here, I can have also with the same set of values, I can also build a binary search tree whose height is way more than log n. In fact, it's something like this, right? So what's the height of such a tree? It's O of n, right? So again, we are in the same situation that its height of a binary search tree can be anywhere between log n and n. In the best possible scenario, it's log n, but in the worst case, it could be n also, right? So if that is the case, so height is within log n and n, right? So all these operations that we're doing, everything was taking height of the tree, right? If in our application we're able to build the tree in a uh, in such a way that its height is log n, then all these operations can be done in log n. Otherwise, all these operations are taking of n time. Okay, is this point clear? So now, can you give me uh, in general, so like if you must have noticed, like the way if we have these many nodes, some n nodes I have, let's say n is of the form 2 to the power some t minus of 1, right? Then can you tell me, if I want to build something like a complete binary search tree, then which element should I make the root? What would be the root if I want to make make the height of the binary tree as log n? Median. Yes, correct. It should be the median. And median will force you half of the element should be going to the left and half of the element will be going to the right. Then what would be the left child of the root? The elements, all the elements that are gone to the left part, I'll take again the median of them. Okay. If you follow that process, you'll be creating a binary search tree whose height is log n. But whereas if you just follow the increasing or decreasing ordering, so I just followed increasing ordering. If I followed the decreasing ordering, then I would be having something tree like this, right? Again, this one also is a height uh, O of n. Right? Let me do one more operation. I'll say successor of a node, successor of a node X. Right. What is this? What is the definition of successor? Smallest value greater than X. In fact, like I'm actually uh, X is the node itself and X is the value. I'm also treating them as a value also. Okay. So for example, so you understand what is this? So successor of a node means that in the whole tree, what is the maximum value uh, uh, which is the maximum value that is smaller than X. Right? For example, let's say in this tree, okay, uh, what is the successor of, let's say, 6? The smallest, which one is the smallest value? Uh, no, successor is greater than. Okay, okay, yeah, yeah, that's I was, yeah, yeah. Yes, smallest value greater than 6. That's 7. Now, uh, for others, say, for example, let's say this. It is very something. Let's say, mm, no, this is not a very good example that I have taken. Okay. Uh, let's discuss in general. So, suppose we have this is the root. Let's say this is the root, and somewhere in this one I have this node X, right? So I want to find the successor of X, right? So this I'm talking in a big binary search tree. Right? This where should this successor lie? Where should this successor lie? So for example, let's say in this one, what is the successor of 17? Successor of the 17. 18 is the successor of 17. And what's the successor of this 14? 15 is the successor, correct. Right? But I want to, in general, so I guess like you, since you can see the overall tree, you can just by looking at this, you can tell what is the next greatest element. than this X, right? But I want to think about the search property and try to think where that successor element should be when you have when you look at any node. X is the node. Where should this successor be? Successor is a element which is greater than X, right? Where should it be? Suppose this one is having, here is another branch, here is another branch, right? Okay. Uh, can that successor be somewhere in here? Can the successor of X be present in here? No. Why? Because all the elements in here are smaller than this. Now, can the successor be present somewhere upwards, somewhere here? Can it be a successor of X? Uh, maybe. Can you tell me in what case this could be a successor? The way I have drawn this, so this one, let me call it somewhere here Y. This Y is appearing, maybe something here. This X is appearing in the left subtree of this. So Y is obviously greater than X. That is true. But what about the elements here? These elements are greater than X, but if I compare it with Y, these elements are less than Y, isn't it? Right? So if this one, if the X is having what can I say? Like if this X is having successor, then it should be in the right subtree of this. The should be in the right subtree. Not only that, we can say something extra also. Right subtree, that's okay. That successor should be in the right subtree. But I can also tell what is the successor of X. So far, we have just argued that successor should be in here, the right subtree of this. Can you tell me which one would be the successor of X? All the elements here are greater than X. And successor is something which is more than X. And out of all those elements that are more than X, successor is the least. Successor is the smallest. So basically, I am looking for the minimum element in here. And where should it be? I'll go to the right subtree and then keep on going to the left, to the left, to the left, and find the minimum of this right subtree. And it's in fact, it's the minimum of the right subtree. Is this clear? Okay. Right. So see, like in this example, that is what happened. Right. Successor of 18 is 20. Go to the right subtree. This is the whole thing. It's a minimum. Right. Successor of 6, this whole subtree, look at this whole subtree, was the minimum there. From here, keep going to the left. That's not possible to go because it's a null pointer. That says 7 is the smallest in the here, right? Okay. But in some case, for example, this 14 or maybe for the 17, right? What is the successor of this? For this 14, it's 15 is the successor. Successor is appearing somewhere above. Like 17, the successor is appearing somewhere here, right? What's the successor for 7? At top in the tree. No, not always on the top of the tree. So, what's the successor of 7? Successor of 7, I'll go to the right subtree. In this one, find the minimum one. It's this one, right? Or when do you think the successor is not in the right subtree? For this example, from this example, can you tell me when can I say that the successor is not there in the right subtree? So when there is no right subtree, if the right subtree of, what's the right subtree of this? Nothing. Right subtree of this, there's nothing. Right. So in that case, the successor should be in the right subtree so that if x has right subtree, then only then the right subtree, then the successor is in the right subtree. And what is that element? That should be the minimum in the right subtree. But what happens if this does not have any right subtree at all? There's no right subtree. Okay? Then let's say in that case, the successor, if it does not have any right subtree, then the successor should be above it. Why? Because it does not have any right subtree. There's no right subtree. All these elements, these are less than x, right? So it should be in the above. If its parent is y and x is appearing as a left child of y, x here is appearing as a left child of its parent, then what would happen? So what can I say at this point? Or can I at all argue anything? Can I say that y is the successor of x? So is this y greater than uh, is this y greater than x? Yes, because x is appearing in the left subtree. So y is more than x. Can there be any other element uh, that is less than y, but also greater than this. What are the elements there? What is the element above it? So suppose this is having something like this, z. The element z is more than, so all the elements in this part is more than y. If y is appearing as a left child of z, then z is also more than y. Right? In the other case, if we have something like this, right, then z, what can you say about z? Z is less than y, right? And also, if in this case, what can you say about x? What is the relation between x and z? The way I have drawn, what's the relation between x and z? X is more than z, right? So x is more than z. So if this is the case, if let me write this case here. If x is the left child of its parent, say y, then successor is y. Okay. Is this clear? There could be another possibility that y, so for example, let me tell you something here, right? What is the successor of 2? There's no right subtree, right? So I should be going here. This is appearing here. So 2 is appearing as a left child of its parent, 3. So its successor is 3. This is the situation I just talked about. But that is not the case for 14. 14 is appearing as a right child of 13. Right? Okay. So that means this 14 is more than 13, more than its parent. So what should I be doing then? I will be checking again parent of this. Again parent of this. And at some point, I will be reaching some value, some node, which is a left child of this, left child of its parent. And that is the value of the successor. Okay, this is a little complicated than the other operations that I have done. So successor means like from here, I'll move to its parent. If this parent and this node is having left child and parent relation, then we are done. Then that is the case. Then I'll report that the parent is the successor of that node. Otherwise, I'll keep on moving up and up and up till the moment the till the moment that node will appear as a left child of some parent. At that point, I can say that this is the successor of that the parent that we have encountered, that's the successor of this node. Okay. So we just think about this. Uh, okay, and let me write it here. Otherwise, keep moving up till node appears as left child of its parent. So in that case, was the successor that parent itself, that parent node will be the successor of that particular node. Right? Okay. The way we define this successor, in a similar way, I can define the predecessor also. So what is a predecessor of X? Is the greatest value smaller than X. Right? Out of all the values that are smaller than X, I'll take the maximum. Now, similar thing will happen if X is here and it has a left subtree. It has a left subtree. Then all the elements here are less than this. All the element in the left subtree are less than this. I have to figure out the maximum of this. So when the maximum will appear at the rightmost part of it. Right. So again, the first step will be similar. Here, what we did, we went to the right subtree and find the minimum there. But this time we have to go to the left subtree and find the maximum there. Right? In this case, it's a maximum of left subtree. Okay? And other things can happen as well. So if this is not the maximum one, sorry, it's not the maximum. So if X does not have any left subtree, then I have to keep moving upward. Right? I have to keep move. I have to keep moving upward till I find something which is till I find some node, this node, which appears as a right child of its parent. Right? What would happen in this case? So X is like this is I'll say Y. What's the relation between this Y and this Z? Let's say Z is more than Y, right? And Y and relation between Y and X is again more than Y because X is appearing in the right subtree of Y. Okay, so that's why we're saying that this Y will be the out of all the smaller values that are less than like all the values that are smaller than X, out of all of them, this Y will be the maximum. Okay, fine. So it's a predecessor and successor is, I think, more or less you have understood this, right? So only one operation. So how much time does this predecessor and successor finding predecessor and successor will take? So if I give you the node, you have to go to the right subtree or the left subtree and find the minimum and maximum. Finding this minimum and maximum can take again height of the tree. Or in some other case, you might have to come all the way back to the top. Okay. So in all of those cases, you might, in the worst case, you might take again O of height of the tree. Okay, so predecessor, okay, so with this example, let's say, was the predecessor? Predecessor, as I defined here, is the out of all the values that are smaller than x, I'll be taking the greatest one, right? So let me ask here, okay, in this example. Uh, okay, so what is the predecessor of 13? So I'll look at all the smaller values, and out of them I'll take the we'll take the maximum. So 13, it has a left subtree. So I'll go to the left subtree. In that left subtree, I'll find the maximum one. Again, something similar. What's the predecessor of 6? I'll go to the left subtree and find the maximum. Yes. Find the maximum in this. So I'll go to the left subtree and maximum is 4. So 4 is the predecessor of 6. Now something different. This 7, it does not have any left subtree. Where should this predecessor be? It should be above it, right? So I'll keep moving up till I find some node appearing as a right child of its parent. The 7 itself is appearing as a right child of this. So I'll be taking that one as a predecessor. 6 is the predecessor of 7. Okay, things will be a little clear when you have. So suppose 8. What is the predecessor of 8? How do you find this predecessor of 8? So it does not have any left subtree. So its predecessor, no, its predecessor is not 9. Predecessor means what? 9 is greater than 8. It cannot be the predecessor, right? You understand this? Right. It's not its parent, right? So it does not have any left subtree. So its predecessor should be above it. Like it's not its parent, maybe somewhere else. So what do I do? I'll go to its parent. And now I check if this node is appearing as a right child of its parent. Is it? Is 8 the right child of 9? No, right? So then I'll again move ahead. I'll check whether this 9 is a right child of 13. Again, no. Right? Now again I'll move ahead. Now I'll see if this 13 is the right child of 7. Yes, 13 is the right child of 7. At that point, I'd say that this 7 is the predecessor of 8. Does this make sense? So we are doing essentially the same thing as successor, just by changing the left to right and right to left and minimum to maximum. Okay. So I hope this is clear now. So I'll take a few extra minutes just to complete one more operation here. And the operation is deletion. deletion of a node. Okay. So there are actually three cases. Two cases are actually simple. Mm, what is the case? So if X is a leaf, okay? So X is appearing as a leaf, right? It may be something here, something. So what are the changes that I have to do? It's just I have to get rid of this link. Right? What is this link? There are two like this Y is the parent of X. I have to cut the parent pointer. I have to set the parent pointer of X to null, as well as this X is appearing as a left child of Y. So I also have to set the left child of Y as null. If I do that, that actually means that I'm cutting this link. Okay, do you follow this? Okay. So this is the really easy case when X is a leaf. Right? What's the other thing? X has exactly what exactly one child. Right? So X is having just one child here. Okay? Let's say this is the child. This is X, right? And its parent is something like this. Right? This is the parent of X. So what do I have to do? I have to cut this link. I have to cut this link, but I have to set up another link. Now this could be a whole subtree here. Okay. So I'll get rid of these two links, but if I get rid of all these things, then this whole portion is out of the tree, is going out of the tree, right? That should not happen. So that's why I have to set up another link here. So I have removed, this one is Y, let's say. I have set left, Y left. I have cut it, right? Now, if this is Z, I have to now set this one as Z. Left child of Y, I'll set it as Z. This link I have to establish. Okay. And the third case is X has both the children. X has both left child and right child. Then what would happen? So suppose this is my X. This node I want to delete from the tree. Right? So it has let's say B as well as let's say C here. Okay, maybe. So what I'll do? How can it may have something above it also. I want to delete this one from the tree. What am I supposed to do? If I delete, then I cannot, so from its parent, I cannot set which one to join, whether to join this B or I need to join this C. Those I have to take care. But rather than that, what we do, I'll find the predecessor. Right? Where this predecessor should be, I just argued, predecessor should be in the left subtree. And what is that? that's the element, maybe this D, right? That's the rightmost maximum in the left subtree. Okay, this could be even bigger, but at this point it ends. It might have something down here. It does not have any right child. D does not have any right child. D is the predecessor of X, right? So what I do, I will take, so I'll find, so say this is D, right? And I'll change X by D. So I'll take this D in here. Okay. So what would happen if I take D in here? Are we violating the search property? D is actually, so out of all of these elements, D is the maximum. So if I put D here, I'm not violating the search property. All the elements, remaining elements in here are smaller than D. Okay. So actually what I'll do, I'll change D by, so change this X by D. I'll put D here and I'll put X here. And now I'll remove this X. So now is this removal of X okay? Now see this, I can remove this if X, now in this case, X has two options only. This X may be a leaf or it has only one child. What child is that? This particular X should only allowed to have a left child when I'm taking X here. So it's again, we are going back to case one. Okay, how much time does this take? Case one, it's just cutting one link. It's O of one time. In case two, it's cutting two links and joining one. It's again constant. But how much time does this case three take? In case three, we have to find the predecessor, right? But that in the worst case can take O of H time. Okay. So overall, this deletion process takes again order of height of the binary search tree. Okay, is this deletion process clear? Any question? Okay, okay. So another interesting property I'd like you to observe that suppose I have a binary search tree, right? This is the binary search tree that I have given to you. Okay. And there are a few nodes in here, few values are there, right? Now I want you to arrange this value in a sorted order. You understand? I want you to sort these numbers. Can you tell me a process by which you can sort these numbers? Yes. What is the sorted order of these numbers? Let's say 2, 3, 4. Then, yes. Then 6, 7, 8, 9, 13, 14, then 15, 17, 18, 20. Right. This is nothing but the in order traversal. So this gives you another way of sorting, right? So you have all the elements, you construct a binary search tree, right? Uh, you construct a binary search tree out of this, and then you make a in order traversal, and that will give you a sorted order of these numbers. And while constructing this binary search tree, you don't have to care about the ordering. You can insert them in any order. Okay, no matter what order you insert it, at the end when you have successfully constructed the binary search tree, then you apply the in order traversal, and that's it. That will give you an increasing ordering of the keys. Okay. Oh, fine. So I'll stop at this point. Any question? All these were covered in our previous one. These things are already covered. Okay, so hopefully, so you have revised things correctly. So and okay, not in depth. Okay, so I think any question at this point? Okay, so have you understood this? Okay, fine. Uh, and I think the heap was also done in the last class as well. Binary heaps, right? Okay. Okay, fine. So there's one more data structure that okay. So what we have seen in okay, so it will be again a repetition of the same thing again. So rather than that, I'd like to move to the graph algorithms in the next class. Hmm? Will it be okay? So we have seen like binary search trees has a nice search property, but it's high. All the operations we can do in order of h, but the height is somewhat. You want height of the binary search tree may lie in between log n and n, right? But okay, so we'll touch upon the heap and then we'll move to the graph algorithms then. Maybe in the Monday's class we'll talk something about the heap and then we'll move to the graph algorithm. Okay, so heap is something where you have uh, okay, so it's no, it's not possible. So heap is something where we can make the height of the tree, binary tree, to be log n, right? We introduce some extra property there. For that, it will be okay, and the height we can adjust. Binary search is best case for time complexity. So which problem you're trying? So you want to search it? Only searching for searching problem, binary search tree is not the best thing because you have to build the tree first. But while building the tree, if you take an increasing order or decreasing order, then the height of the tree will be O of n, right? In that case, again, this running time will be O of n, not O of log n. Okay. Somehow you have to construct this binary search tree in such a way that it height becomes log n. If you can do that, then only you are gaining some. And heap is such a data structure which allows you to maintain the height of the tree to be log n. Okay, I'll discuss it in the next class. Okay, so then I'll close this meeting now, and after a short break, TA will help you in this coding part. Okay, thank you.